is a quiet assumption we make every single day.
We trust that the ticking of the clock on our wall matches the watch on our wrist. We assume that there is a universal now, a shared stage, a master clock, ticking in the background of the cosmos, perfectly synchronized for me, for you, and for a rock floating on the other side of the galaxy.
It feels intuitive. It feels like common sense.
But it's a fiction. To understand the cosmos, to truly see reality for what it is, we have to let go of this idea. Time is not absolute.
The first crack in this illusion appears when we simply look up. When you look at the stars, you aren't seeing them as they are right now. You are seeing them as they were. The light from our sun takes about 8 minutes to reach your eyes. The light from next nearest star takes over 4 years.
Light is the ultimate messenger. Everything we know about the universe is information carried on the back of light. Albert Einstein was only 16 years old when he started obsessing over this. He used to daydream about what it would look like to run alongside a beam of light.
He wondered if you could run fast enough at exactly the speed of light, would the beam appear frozen next to you, like a frozen wave of water? Classical physics said yes, but the laws of electromagnetism said that light absolutely cannot freeze. It always has to keep moving. This paradox haunted him for 10 years because it meant there was a glitch in the very code of reality. Think about how motion normally works. If you are driving down a highway at 50 kilometers an hour and someone passes you at 100, from your perspective, they're only pulling away at 50 kilometers an hour. Speeds are relative. They add and subtract depending on how fast you're moving.
But light refuses to do this.
In a vacuum, light travels at roughly 300,000 kilometers per second. We call this constant c. If you were to build a spaceship and chase a beam of light at 99% of c, you might expect to look out the window and see the beam creeping ahead of you very slowly.
You wouldn't. If you measured that light beam from your hyperfast ship, it would still be racing away from you at 300,000 kilometers per second. No matter how fast you chase it, no matter how fast you run away from it, the speed of light never changes.
This is a massive problem. Speed is just distance divided by time. Kilometers per hour, meters per second.
If the speed of a light beam absolutely cannot change regardless of who's looking at it or how fast they're moving, then the math is broken unless something else changes.
Einstein realized that if the speed of light is completely rigid, then the stage it moves across has to be flexible. Distance and time are not fixed absolutes. They are variables. They bend, they stretch, and if you move faster through space, your ruler actually shrinks. Your clock physically ticks slower, all to ensure that if you try to measure a beam of light, you'll always get the exact same number.
Space and time are not just a background, they're a single woven fabric. And as we're about to see, this fabric is incredibly sensitive to motion. So light refuses to adapt. It refuses to slow down or speed up for anyone. That leaves a massive problem, because if speed of light is completely rigid, something else has to give. What gives is reality. Space and time aren't a rigid stage. They negotiate.
To understand how this negotiation works, you have to realize something profound about your own existence. Right now, as you sit watching this, you feel stationary, but you aren't. You are hurtling through space-time at the exact speed of light.
It doesn't feel like it, because right now, almost all of your momentum is aimed toward the future.
Think of space-time as a fixed budget. You only have a certain amount of velocity to spend. When you are sitting perfectly still in your couch, you're spending your entire cosmic budget moving through time. Your clock ticks normally. But when you get up and walk across the room, or get in a car, or fly in a rocket, you divert some of that velocity away from time and put it into space. The faster you move through space, the less speed you have available to move through time. This trade-off is the mechanical heart of special relativity. We call it time dilation. Imagine you build a ship that can travel at 99% the speed of light. You have spent almost entire cosmic budget on a spatial movement. Therefore, your movement through time has to crawl to a near halt. To you, inside the cabin, everything is mundane. You pour a cup of coffee and it arcs perfectly into the mug. Your heart beats at a steady rhythm. You age normally. But outside your window, time is slipping.
If you take a round trip to a star system 10 light years away, at that speed, you might spend a couple of years on the ship. You read some books, you miss your family. But when you land back on Earth and the airlock opens, decades have passed. Everyone you knew has grown old. Many have passed on. You haven't just traveled through space, you have exiled yourself into the future. That is the terrifying beauty of time dilation. The time is entirely your own. It doesn't care about the people you left behind.
And it gets stranger. The speed is just distance divided by time. If your experience of time is warping, the physical space around you has to fold to keep the math balanced. As you move faster and faster, the universe itself physically squishes in the direction of your travel. Because you are moving so fast, chasing the light ahead of you, the field of stars appears to gather and clump together directly in your path. Then the colors shift. The light waves ahead of you are violently compressed, shifting into a blinding blue. The light behind you is stretched out, fading into a ghostly crimson. You are no longer flying through a static painting of a galaxy. You are surfing a physical, compressed wave of reality. A journey that looks like 10 light years to the people on Earth physically shrinks down to just a few months of actual distance for you.
Reality is subjective. Your measurement of a meter and your measurement of a second depend entirely upon your speedometer.
So, why not push the throttle? If time slows down and distances shrink, why can't we eventually reach the speed of light? Because the universe protects its speed limit, and it does it by weaponizing your own energy against you. In 1905, Einstein realized that energy and mass are interchangeable, two sides of the same coin. E equals mc squared. Energy equals mass times the speed of light squared. When you pump energy into your ship's engine to go faster, that energy literally becomes mass. Energy of motion adds weight to the ship. The faster you go, the heavier your ship becomes. The heavier it becomes, more energy you need to push it. As you get incredibly close to the speed of light, your ship's mass approaches infinity. It would demand an infinite amount of energy just to push it that final fraction of a percent.
The universe locks the door. Speed of light is completely unreachable for anything that carries mass. But this entire picture is still incomplete because so far we have been talking about a universe that is completely flat and empty, and our universe is anything but empty.
By 1905, special relativity was a triumph. It beautifully connected space, time, mass, and energy. But for Einstein, it wasn't enough because there was a glaring, nagging problem with it.
Special relativity only worked in a vacuum. It only applied if you were moving at a constant speed in a perfectly straight line through an entirely empty universe. And as you might have noticed, our universe is not empty. Things don't move in straight lines. They speed up, they slow down, they crash, they orbit. The real universe is ruled by gravity.
And this is where Einstein found himself at war with the ghost of Isaac Newton. For over 200 years, Newton's laws were absolute. Newton said that gravity was a force, an invisible tether connecting any two masses instantly across the entire cosmos. But Einstein had just proved that the speed of light was the ultimate cosmic speed limit. Nothing can travel faster, not even gravity. If the sun magically vanished right now, Newton's math said the Earth would instantly fly off out of its orbit. Einstein math said we would know for 8 minutes. The gravitational wave would have to travel to us at the speed of light. Someone was wrong.
Einstein knew he had to rewrite gravity. He thought it would be a quick fix. It took him 10 years. It was a grueling, agonizing decade. He had a physical intuition. He could see how the universe should work in his head.
But he didn't have the math. He was trying to describe a universe that physically bends and curves using math designed for flat sheets of paper.
He was so stuck and so stressed, he started developing stomach ulcers. He famously reached out to a college friend, a mathematician named Marcel Grossman, and pleaded, "Grossman, you must help me, or else I'll go crazy." Grossman introduced him to a totally new kind of mathematics, the geometry of curved surfaces. And armed with this new language, Einstein finally found his way back to a daydream he'd had years earlier, what he would later call his happiest thought.
Put yourself inside a windowless elevator, resting on the surface of the earth. You feel your weight pressing down against your feet. If you hold out a wrench and let go, it falls to the floor. Now imagine that same elevator is floating in deep, empty space. Suddenly, a rocket on the bottom ignites. It pushes the elevator upward, accelerating at exactly 9.8 meters per second squared. Inside that box, you would feel yourself pressed against the floor. If you let go of the wrench, the floor of the elevator would rush up to meet it, exactly as fast as it fell on Earth.
Without a window, there is absolutely no physical experiment you can do to prove whether you are resting on a planet or accelerating in a vacuum. To your body, gravity and acceleration feels exactly the same. Because according to Einstein, they are exact same thing.
This is the equivalence principle, and it forces us to accept something totally bizarre. If you fire a laser across that accelerating elevator, the floor is rushing upward while the light travels across. To you, inside the box, the beam of light appears to bend toward the floor. Well, if gravity and acceleration are the same thing, then gravity must also bend light.
But light has no mass. How does gravity pull on something with no mass? It doesn't.
There is no invisible rope. Gravity is simply the shape of the space you are moving through. Mass physically bends the fabric of the universe. When light curves around a star, it isn't being pulled, it's just driving on a curved road. The Earth isn't tethered to the Sun. The Earth is just coasting. It is trying to travel in a perfectly straight line. But the Sun is so unimaginably massive. It has walked the space-time around it into a steep, deep valley. Earth is just rolling along the slope walls of that valley, trapped in a cosmic bowl of curved reality. As the physicist John Archibald Wheeler put it, space-time tells matter how to move. Matter tells space-time how to curve.
This is general relativity. The stage of the universe is physically molded by everything inside of it. Every planet, every star, every galaxy. But that brings us to a terrifying question. What happens when you pack so much mass into a single point that the fabric of reality simply gives away?
All this talk of accelerating elevators and surfing light waves, it sounds completely disconnected from reality. It sounds like a mathematical fever dream that only astrophysicists have to worry about.
But it is not. Einstein's equations are right here in your pocket. Every time you open a map app to find a coffee shop or to navigate through traffic, you're relying on a network of global positioning satellites. And for that system to work, it has to actively manage a war between special and general relativity.
These satellites are moving fast, about 14,000 kilometers per hour. We know from the special relativity that because they are spending so much of their energy moving through space, their onboard clocks have to tick slower than ours on the ground by about 7 microseconds a day. But there is a catch. The satellites are orbiting 20,000 kilometers above the surface. Up there, Earth's gravity is weak, and we know from general relativity that gravity slows time down. So, because the satellite is free from the heavy pull of the Earth, its clock actually speeds up by about 45 microseconds a day.
So, the speed slows the clock down by 7. The weak gravity speeds it up by 45. The net result? Clocks on GPS satellites are constantly drifting into the future. They tick 38 microseconds faster every single day compared to the phone in your hand. If software engineers didn't program the phone to constantly correct for this relativistic time travel, the errors would compound rapidly. By tomorrow morning, your GPS would be off by over 10 kilometers. This modern world would physically break down without Albert Einstein.
The math that guides you to a coffee shop is fiercely accurate. But what happens when you take that exact same math and you push it? What happens when you feed it numbers so extreme that the fabric of reality simply gives up?
When a massive star dies, its core collapses inward. If the star is heavy enough, there is no force in the universe strong enough to stop that collapse. The mass condenses and condenses. It warps the fabric of space-time so violently that it punches a hole straight through the floor.
Pop culture likes to treat black holes like cosmic vacuum cleaners, sucking up everything in the galaxy. They aren't. They're just potholes, indefinitely deep potholes in the geometry of the universe. Because the space is warped so steeply, the speed required to climb out of that well is greater than the speed of light. And since the universe strictly enforces its speed limit, nothing can ever climb out. The boundary where this happens, the absolute edge of the abyss, is called the event horizon. If you were to watch a probe or a person fall toward that horizon, you would witness the most terrifying consequence of relativity. Remember, intense gravity slows down time. As your friend gets closer and closer to the edge, diving deeper into the gravity well, their clock begins to slow down relative to yours. To them, flying inward feels perfectly normal. But to you, watching from the outside, they appear to slow down. Their movements become sluggish. The light bouncing off them struggles to find its way up out of the gravity well. It loses energy. It stretches out, shifting into a deep, ghostly red.
You would never actually see them cross the edge. To your eyes, their time would stretch, slow, and eventually freeze entirely. Their image would remain there, etched into the event horizon, fading into the dark infrared spectrum over thousands of years.
But what about their perspective? Falling in. Time inside their suite feels fine. But looking back out at the universe, they see the exact opposite. Because their time is running so slowly, the rest of the cosmos appear to hit fast forward. In the final moments, before crossing the veil, they could look back and watch the entire future history of the universe play out. Stars being born, galaxies colliding, fading into a blinding flash of light.
It is a place of ultimate isolation, a place where the laws of space-time, as we understand them, fold in on themselves and collapse. It forces us to confront the very limit of human knowledge.
When you step back and look at the whole picture, general relativity is staggering. From a handful of equations, one man essentially rewrote the operating system of the heavens. We used to think of time as a master clock, ticking away universally in the background. Einstein provided it's personal. It belongs entirely to you. It depends on your speed and the gravity you happen to be standing in. Space is not an empty box where things happen. It's a physical woven fabric. It reacts. It bends. This theory works perfectly. It guides the satellites in your phone. It explains the dance of the planets. It predicts the terrifying abyss of a black hole. It is a flawless map of the macro universe.
Until you look too closely.
If you zoom past the cells in your hand, past the molecules, down to the scale of electrons and quarks, Einstein's smooth geometry completely falls apart. The universe down here isn't a gentle curve. It's a violent, jittery, unpredictable storm governed by an entirely different rulebook: quantum mechanics.
And this is the greatest unsolved mystery in modern physics. Quantum mechanics works, general relativity works. Both have been tested to extraordinary precision. But if you try to combine them, the math shatters. They refuse to cooperate. At the smallest scales, space-time should be frothing and fluctuating. But general relativity describes it as smooth and continuous. We are left with two maps of reality, both fiercely accurate, but completely at war with each other.
this is the frontier. Somewhere in the math, there must be a bridge, a theory of quantum gravity that can finally connect the physics of the unimaginably large with the physics of impossibly small. Thousands of brilliant minds are searching for it. Some are smashing particles together at CERN, listening for whispers of new physics. Others are watching the fabric of space-time itself ripple at LIGO, hoping to catch the echoes of the universe's most violent moments. We don't have the answer yet, but until we find it, we can simply look up, not at a rigid sky with distant lights pinned to it, but at a magnificent, curved, living stage. A stage where your time flows differently than mine, where mass bends the path of light, where black holes hold the future frozen in their event horizons. A stage that is full of secrets.
Thank you for tuning into Antariksha. My name is Nikhil, and I'm really glad that you watched it this far. If you liked it or even disliked, then please leave your thoughts in comments down below. Do not forget to subscribe to get more such stuff about science. Your presence is appreciated.